This lecture is part of an online course of Calculus 1, and I'm going to talk about the Squeezed Theorem. Let me state the theorem first. If we have three functions, f of x that is less than g of x, and g of x is less than or equal to h of x, near x equals to a. What do I mean by near x equals to a? Basically, I mean for all x, not necessarily a is one of those, in an open interval containing a, which means that I have an interval that a is in that interval, and then on all the x's on this interval I have this inequality. And if the limit of f of x as x goes to a is equal to L, and at the same time the limit of h of x as x equals to a is equal to L, which means that the limit of both ends, f of x and h of x, both of them are equal to each other and they're equal to L, then we have the limit of the function that is in between g of x as x equals to a. This is also equal to L. Okay, so that is the Squeeze theorem. Let me explain it on the shape. So this is x-axis, this is y-axis, and this is basically a. So I have a function like this. This is g of x. And g of x is basically between h of x and f of x. So h of x and f of x are basically bounding g of x. And as you see, the limit of h as x goes to a from right and left, this limit of f as x goes to a from right and left, both of them are equal to L, and so the limit of g is also equal to L. Okay, so how can we use a Squeeze theorem to find the limit? Let's look at one example. If we've been asked to find the limit of x squared sine of 1 over x as x goes to 0, we want to see what is this limit. Let me actually show it to you. Okay, the function is right there. Let me basically show the function a little better with a different shape. This is the function y equals to x squared sine of 1 over x, and near 0, if I zoom in, you see the function is basically bouncing. It's going up and down, but is it getting closer to 0? We need to see. Okay, we need to evaluate. You see, I'm just trying to see. It looks like that the limit is going to 0, but let's see. Let me prove it. So as the solution, first let's plug in x equals to 0 into the function and see what we get. We get x squared sine of 1 over x as x goes to 0. As you see, this limit, because the sine of 1 over x does not exist, we can not actually use the product law for the limit, because as you see, the limit of x squared when x goes to 0 is equal to x, and the limit of sine of, let me write this, sine of 1 over x as x goes to 0. What is this limit? I get the sine of 1 over 0. I explained in the other video that when we have a number over 0, this limit does not exist. So it does not exist. And that's the problem, because I cannot use the product law. For the product law, the limit of two functions that are multiplying to each other, the limit of both of them should exist. But in this case, the limit of this one does not exist. So that's why I cannot use the product law. So let me use a Squeeze theorem. We actually know that the sine of anything with any angle, the sine is between 1 and -1. Why is that? Because of the graph of sine. See, x-axis, y-axis. This is sine, and as you see, sine is always between -1 and 1 for any angle. Okay, now I'm gonna use this fact, and I'm gonna multiply the whole inequality by x squared. So I get x squared times -1, so negative x squared is less than or equal to. X squared is a positive number, so that's why I'm not gonna change the direction of my inequalities. And then I get x squared sine of 1 over x, and then I get 1 times x squared. Okay, now I get my function. This is the function that I want to find the limit between two other functions. Now let's see, the limit of the first function as x goes to 0, just it's a polynomial, plug in 0, I get 0. And also the limit of the second function, the second bound, x squared as x goes to 0, this is also equals to 0. Now let's look at the Squeeze theorem. If the function is between two other functions and the limit of two bounds are equal to each other, then the limit of the function that is squeezed between them is the same as those. So I get the limit of both of them equal to each other. So I can say by Squeeze theorem, I get that the limit of x squared sine of 1 over x as x goes to 0 is equal to 0. Okay, that's how I prove that the limit, this limit exists and it's equal to 0. Let's look at another example. Example is this. Use a Squeeze theorem, to find the limit of x times cosine of x as x goes to 0. Okay. Well, let's see. I can use product rule, using product law, actually we call it the product law for limits, and I say the limit of x cosine of x as x goes to 0. I have a function in here, I have another function in here. It is the limit of x as x goes to 0 multiplied by the limit of cosine of x as x goes to 0. Am I allowed to do that? Yes, because this limit exists and it's equal to 0, and this limit also exists because I can plug in 0 into here. I get cosine of 0, which is 1, so the answer is 0. Okay, now instead of using product law, let's use a Squeeze theorem. So let's use Squeeze theorem. Well, we know that cosine of anything is between 1 and -1 based on the graph of cosine. We know that. Now I'm gonna multiply the whole inequality by x, so I get -x cosine x, and I'm gonna multiply 1 also by x. Now since the limit of the bound -x as x goes to 0, it's equal to 0. It's a polynomial plug-in 0. And it's also equal to the limit of the other bound, this one, as x goes to 0. Since both of them are equal to each other and they are equal to 0, then by Squeeze Theorem, we get the limit of the function that is between these two, between this and that. The limit of this one is also equal to 0. And as you see, the answers matches. We usually, as you see in these two examples, use Squeeze Theorem for not algebraic functions to find their limit. If we have algebraic functions like addition, subtraction, or product of just polynomials, they're easy to do, and we can just plug in the limit into there, the point into there, and then find it. But in this case, for example, I cannot do that because one of the sides of the limit does not exist, and that's why we use a Squeeze theorem to solve it.